So good morning, everybody. Thank you for joining us. My name is Joe Carrock. I am a field applications engineer with Telops. And today I have a webinar for you titled First Results, Midwave IR Assessment of Hypersonic Models in Flight. Before we get going with that, we would like to poll you briefly on your experience with IR imaging. If I can go ahead and launch this poll right here, you should see that on your screen. We hope you would answer that for us and let us know whether you are a thermal imaging expert or if you might have a little bit less experience or no direct experience even with infrared technology. This helps us gauge the level of our audience so that we can make better presentations in the future. We do have a pretty large group today, so this should be a pretty good indication. Let this run for just a few more seconds and then we will share and we can look at the results together, I believe. Just a few more seconds, we'll let it run. It seems like some votes are coming in at the end. Okay, so I will end and share the results here. I hope you can see that on your screen. So we have a pretty good mix. A lot of folks seem to have direct experience, but not exactly calling themselves experts. I wouldn't sell yourself short. I bet this is a pretty knowledgeable group. And that makes sense because this is a pretty advanced topic, but I do think we'll have something for everybody today. And of course, if you do have questions or if there's something you don't understand, please reach out. My contact is here on this first page, but it'll also be several places throughout the PowerPoint. So go ahead and close that and get back to our main screen. And we'll get going. So yeah, this webinar is about some results that we've now collected with our Midwave IR stop motion variant camera that we've created primarily for hypersonics, but we do think it has a lot of other application potential as well for all measurements that might need to stop motion of a projectile or a target. And yeah, so this is sort of a part two, sort of an update webinar to one we did just about a year ago, where we discussed the need for this camera and our plans to build it. And in the year since, we have now built this camera. We do have our demo unit that is a complete working stop motion camera. And we have collected some results with some of our partners in their labs. So that's what we're looking to share for you today. We'll do a little bit of background as well as talk about some of the results of the custom multi-point calibration that we put on this system. It's really the power behind what makes it work. And then we'll show those results before wrapping up. So with that, I will jump right into it. Oh, gotta click on the right screen. There we go. So a little bit of background, right? Infrared imaging applied to hypersonics. Optical imaging has long been used in ballistic ranges, especially hypersonic ranges, due to its non-contact nature and its ability to assess the projectiles in flight before they often terminate and are otherwise irretrievable. We see a lot of visible spectrum cameras in these ranges, doing techniques like Schlieren imaging, shadowgraphy, some ultra high-speed systems, things that exceed what infrared camera frame rates can achieve. And we see less infrared imaging in these labs. Some of it is due to that frame rate, those frame rate considerations, which I'll talk a little bit more about on the slide. But we believe that there is a clear need for infrared imaging in these labs, in these ranges, and these experiments. For temperature information, obviously, that can only be provided appropriately in the infrared. But also, the infrared allows us to view things like turbulent structures and boundary layers there within, which are difficult, if not impossible, to visualize with a visible spectrum camera. So we knew there was a clear need for a hypersonic solution, and we started to work out some of these problems. The first of which, like I mentioned, is frame rate. So IR camera frame rates are at maximum on the order of tens of thousands of hertz, and this requires windowed operation. But even then, it's not necessarily great for hypersonics because you might have one on-target frame, but before the camera wells can reset and you can take a second frame, that projectile will be long out of view unless you're using something like a tracker. So high-speed IR cameras with their tens of thousands of hertz are great for events on the order of milliseconds, hundreds of milliseconds, things like wind tunnels, but they are far less good for hypersonics. So we decided to circumvent this by going with a stop motion solution. So you do only get one frame, but we've chosen, as you'll see, an HD detector, so you do get a lot of on-target pixels, and you can get some pretty impressive imagery of this target as it is in flight. Um, and so the second consideration, other than speed, that is a challenge is calibration of the data. So when we have to run ultra short exposure times, the types of things that are necessary to stop these fast moving projectiles, sort of freeze them in motion so that we can image them properly, um, you don't get a lot of signal. Basically, they do not emit enough signal in that time frame to give you good detector performance. Unlike visible spectrum imaging, you can't just flash it with light, or in this case, thermal signature. We really do need to collect that signature directly from the target. And so calibration is a key component of this. And coincidentally, or I guess unfortunately, detectors do not perform well under these conditions. They do not perform well at minimum exposures. We'll talk about that on the next slide here. But essentially, we had to develop a custom scheme, a custom calibration to be able to retrieve interesting, useful data when operating the camera under these extremes. And again, so why is it difficult? It's typically because of signal levels and the fact that midwave IR cameras are generally geared towards seeing things that are at room temperature, ambient temperatures, or on the order of a couple hundred degrees C, where you can use exposure times of up to, on the order of 1 millisecond, 1,000 microseconds, relatively long on the scale of what we're talking about here today. You obviously need to go quite a bit shorter to achieve stop motion imagery. And then we run into two problems there as well with the signal level. So we're receiving less signal from the target, obviously collecting for a shorter exposure. But then we have to worry about that signal level, and we need to keep it between two thresholds. So the first of which is pixel saturation, which you might be familiar with. Pixel saturation is when the wells are actually full of photons. The photons have exceeded the capacity of the pixel, and it needs to reset itself before collecting any useful information. But we also have to worry about photocurrent saturation, which is when the flux of photons, or the rate at which they're coming in, exceeds what the detector can handle. So it's not necessarily that the wells are full, but that the rate of photons is too high. Together, these two types of saturation essentially give us a floor and a ceiling signal level that we must sort of manage. We must slot in between in order to get good data, even with this custom calibration, this custom multi-point calibration that we've applied to our stop motion midwave IR camera. So there's a lot more information on this in our first edition webinar, the one we did about a year ago, as well as in our SPE defense paper on the same topic. So I encourage you to go look those up if you'd like more information on why we made the choices we did and how we constructed this camera essentially. But for now, I'm going to move on to talk a little bit more about the calibration itself and the specs of the camera. So we settled on our M3Shd camera because the detector performance was excellent. The detector is very sensitive even at these low signal levels, but also because it's an HD detector. So if we're only going to get one frame, if we're only going to have this one stop motion image, we might as well have good spatial resolution. And the 1920 by 1536 pixel detector is the largest that Telops offers. It's one of the largest HD IR cameras available, and that's great for this purpose. And so, because that camera has that large detector and is good performing, sensitive, we were able to do some firmware adjustments and make this multi-point calibration, custom multi-point calibration with two temperature ranges that you can see there. 150 C up to 550 C is the lower temp calibration. The cut-on being about 150 C to get the minimum amount of signal we need to appropriately calibrate. And then 350 C to 1500 C is the high temperature calibration. That is completed with an OD1 filter, a hot OD1 filter in the optical path. And with that calibration, we can get pretty good accuracy and non-uniformity specs. So accuracy is less than 10K at 1,000 degrees C, and residual non-uniformity is less than 5K at a 1,000 degrees C scene. Both of those are very good especially for the signal levels we're talking about here, and under the conditions that we're trying to push this detector. It's really to its absolute extremes. So we're pretty happy with that. And of course, those values are with exposure times down to 100 nanoseconds, extremely short. And we can calibrate at multiples of 100 nanoseconds here. little bit more information on that as we jump into the calibration. So one more slide on the ranges. So the calibration range there, 150C up to 550C and 350C up to 1500C. And you can see the uniformity there. That's a 1 pixel calibration sample in the plot. Because this detector actually performs so well, we've actually exceeded our own expectations. And for the first units that we are delivering later this month, actually before the end of 2025, we've actually been able to extend those calibrations downward on the low end. So we can actually see lower temperatures in either of those calibrations. We're not ready to fully put it on the spec sheet yet, but the actual models that we're delivering have wider ranges than that, which we're pretty proud of. So a little bit more on the noise specs and the error specs. So this is a test that we did on this calibration that is on our demo unit right now with precision black bodies, excuse me, up in the factory in Quebec. And so as you can see, even with the 150-degree black body, so that is the coldest that we were calibrating to at the time, the least amount of signal that the camera receives. We can see that the accuracy is around 1K, the spatial noise is around plus or minus 1K, and the temporal noise is a little bit even better at 700 millikelvin. And this is at a 1 microsecond exposure. But we're very happy with that. So it essentially means that the camera is accurate to the reference source, to the black body. Its temperature reading is accurate. Spatially, across the pixels of the detector, it is accurate, and also temporally. So over time, the fluctuations in noise are relatively small, meaning we have good data in all conditions. And one last slide here on the calibration. So here is the error for different exposure times, as well as across the temperature range of our 2 calibrations. And as you can see, it stays within spec. It does fluctuate a little bit. There is, a good amount of detector non-uniformity that we are contending with, but we are very pleased with the performance of this detector, as well as the calibration we've applied and its usefulness in terms of radiometric accuracy. And so with that, I will now quickly jump into the fun part. So the results that we've been able to collect. So since we built this camera earlier this year, several different labs have invited us out, including some folks that we've been talking to about this camera for multiple years that have helped us develop it. And they've invited us to collect data. So far, we've had multiple successes, including some that were so successful, the data quickly became too secret for us to share with you here today. So we're really happy to show this stuff. And here's our first example. So this is from Texas A&M. So Dr. Jack Shine, who is actually part of the BAM lab, is a contact that we've been talking with for a couple of years at this point about developing this system. And when we had this demo unit ready to go, he invited us down to image in the high velocity impact lab of Dr. Thomas Lacey. They have a 2-stage gas gun down there at Texas A&M. And as you can see in the top right, that is our image that we collected, our stop motion image. That is a polycarbonate cylinder, half an inch in diameter, that was imaged at Mach 20. Yeah, that's right, Mach 20. Those guys at Texas, they really like to shoot fast down there. Very impressive that we were able to capture this. This was actually the first shot that we ever captured with this camera. So you're sort of just waiting and hoping that everything works out, and then you trigger it properly and it comes up on the screen, and how amazing it was. So we're very happy with this. One more comment about the orientation. So this is actually off a mirror. So we shot a cross range onto a mirror, and then up range. We were hoping to image the front face of this projectile, but as you can see, it's sort of tumbled. So especially for these cylinders and projectiles that fly a little bit more irregularly, they may tumble, which means that we can't see the front face of the projectile here. We're only seeing the sidewall, as well as the wake and the column adhesion there of the air. So this is something to think about when we're talking about signal levels, right? And signal ceilings and floors that we need to slot in between. Depending on how this projectile tumbles, there's going to be a lot more signal from that front face if it happened to tumble into view. And this is one challenge, right? These events are not entirely predictable, especially in flight. These projectiles, they won't always perform the same. So multiple challenges here, even now that we have this nice tool and this great camera that is able to provide us with these great images. Still a lot to think about, but you'll see, right, so on the bottom right, I have zoomed in a little bit on this image up here. And that is, you can see all the pixels that we have. That's just one hotspot on the sidewall of that. And with this HD detector, we have a whole lot of temperature gradient information It's far more than just a few points to average. So we're very pleased with that, and we thank Texas A&M for having us out. Interestingly, they will also be receiving one of the first units of this camera before the end of 2025, and we hope to collect a lot more great data with them going forward. So one more example that we have, and this is an even prettier picture from from Case Western Reserve University. This is the lab of Dr. Brian Schmidt, the HOP Light Lab out there in Cleveland. And this is by far the most stunning image we've collected with this camera to date, even of the ones we can't show you. This is a Delrin cylinder that was fired at Mach 9, so a little bit slower, but still captured at 500 nanoseconds. And among the reasons for improved clarity, other than the slower speed, we are also imaging directly on target. So we're actually looking up from underneath the chamber right now at the projectile as it's in flight, and it's sort of moving north to south here on the image as it progresses. And in addition to getting the front face, obviously, we have the front face fully in view there and the full temperature information. We also have the sidewall and this prominent wake that we theorize is visible due to pyralization of the Delrin. So there's actually hot particulate that is pyralized off the cylinder there that allows us to see those turbulent structures there in the wake. And that was truly amazing to us. As soon as we saw that, that is something that you can't easily visualize in the visible spectrum. And we weren't even expecting it to be so prominent, but it is. This IR camera and this technology and this ability to see these low signal levels in this stop motion fashion are truly amazing. We're still learning about all that it can do. So here's a little bit more of a breakdown on the temperature gradient information. So this is all stuff that you can do right in our software after this data is collected. These are just line profiles of radiometric temperature. And you can see there that having all these extra pixels, you can really see the differentiation in signal. I wouldn't even necessarily call this gradient uniform in certain places. There's unique features there. Certainly a one number average would not suffice to explain what's going on. And this camera, with its high spatial resolution and its stop motion imagery, is able to capture those moments for you and give you those actionable data points, even after the projectile is long gone. So in addition to temperature, again, we were talking about the wake. So one more comment I'll make about that, right, is we can see this sort of pattern here. It's periodic. It's almost sinusoidal. And just going in with spatial resolution information, we were able to figure out that period on that flow there is on the order of 12 millimeters, a little bit more than 12 millimeters per cycle. So that's really interesting, and obviously a piece of information that we would have otherwise had no way to capture. So stunning images, great data points, all very interesting stuff that these labs are very happy to have and to work with going forward, and we're very happy to be able to provide that for them. So that's the data we had to share today. Again, I will let you know that this camera right now that we've built this year, an M3Shd with a 1920-1536 detector and exposure times under 1 microsecond, multiples of 100 nanoseconds, is performing extremely well. And we are now offering it as a custom solution in this configuration that I've shared today. And we are delivering the first units actually of that custom solution before the end of 2025. So this is available now essentially in this configuration, but we will also be working to release a catalog option for standard systems which are able to perform at these ultra low exposures before the end of 2026. But we will also mention that customization is always available. And like I said at the beginning, we do see other applications where this might be a good technology to apply as well. Things like cold spray additive manufacturing, machining, viewing processes in sequence. So please do reach out if you have any interest in this technology, this system, or a similar variant that you might be able to dream up. We'd really like to talk to you about it. And so with that, I will move to close. Again, we have this new system, this new tool for hypersonics ranges to capture optical assessments of hypersonic projectiles in flight in the infrared. Now we have proper results to share with our lovely partners at TAMU and at Case Western. And we've been able to provide excellent data for them with temperature gradients, being able to visualize the turbulent structures they're in and the wakes and such. And we do plan to continue this work. So we have more collections upcoming. We just actually did a collection for cold spray additive manufacturing with this camera last week that we're pretty excited about the data. And we'd also like to work with all of you. So whether you have a hypersonic range or not, please take our contact information there and let us know what you're working on and what you might like to work on with us. We'd be happy to help you advance your research and hopefully the field of hypersonics or other fields in general. So yeah, with that, again, email us. If you would like to talk about the specs of the system or the performance or your application, you can obviously email me there with my email. But if you'd like a demo of the system or pricing, go ahead and email sales@telops.com, and we will be able to get you connected with the appropriate representative for your region. Okay, so thank you for joining us today. Thank you for listening. I know that was a little brief, but you know, with stop motion images, they're just single frames. So please do reach out if you'd like to see anything more there, if you'd like more information about the data I've just shown, or if you have any anything that you'd like to talk to us about going forward. And I hope there are some questions here in the question chat box. I'll give a few minutes for some more of those to come in. If anybody has come up with any questions here at the end, I'll go and take a look at that right now. Okay, so there's one question here about the trigger on the cameras. I think that was on a slide. I might have failed to mention it. So the triggering system for all Telops cameras, it accepts a TTL trigger, a 3 or 5 volt square wave signal, and it performs extremely similarly to any visible spectrum, high performance visible spectrum cameras you may be familiar with. When we have been going into these ranges in labs, we've basically been running the same trigger lines, the same trigger system that they've been previously running to their visible spectrum cameras to the Telops camera, and it performs just as well. It almost no issues. I think we spec the trigger jitter for our cameras at about 1,000 nanoseconds plus or minus 300 nanoseconds, which might sound like a lot when you're talking about 100 nanosecond exposure, but it's actually very minimal in the sense that it will only cause the projectile to shift a couple of pixels in either direction on the FPA in that jitter. And we've had no trouble basically centering the projectiles as you've seen using standard math to do the timing. Thank you for that question. We'll see if there's any others in here. Which camera models will there be? Okay, so which camera models will we be applying this to? I think the question here is asking if there'll be a long wave model eventually. So it'll essentially be whichever detectors and electronics can handle operating at these extremes. So we would like to make different models, different FPA sizes, different band passes. But at this point, to push these cameras to these extremes, it's limited more by the actual hardware itself and the performance of the detector and the readout electronics than it would be us just choosing what we would like to do. So we hope to, but I can't speak on that yet, whether or not which systems will be included in our final standard catalog offering. Okay, I think that seems to be it for now in terms of questions. Again, I'll go back one slide here if I can, just to give you our email one last time. Please do reach out. Please do send your questions there in the coming days if you think them up. And we hope to hear from some of you folks. We would love to collaborate with you and help improve the tools that you have available for your research. So thanks again. I appreciate you joining us today, and have a great one.